I'm going through the 4.2 lesson, examples 1, 2, 3, and 4. And this we're talking about acid-base solutions and how to do the calculations. And I put a little picture here to remind us about the demonstration we did before we got to here, because different solutions would have different pHs based on what's dissolved. Acids or bases, or weak acids, strong acids, weak bases, strong bases, and also different salts. But let's start here. So the first one we're saying is, okay, let's say we had a 0.1 molar HCl solution. So we say, well, that is a strong acid. Okay, and so the strategy is going to be, let's find the H plus concentration. And then once we have that, we can find the pH. We can also define the OH minus concentration. And then we can find the POH. And we want to figure out the percent ionization based on all that. So if it's a strong acid, that means that the HCl completely breaks up 100%. That's the definition of strong acids. And we're going to get H plus ions, and we're going to get chloride ions. And we use a single arrow because it's only a one-way reaction. We could do an icebox for this. And we say, well, we have a 0.1 molar solution and 0 of anything else. And we're going to say if it's strong and it all breaks up, then this change is minus 0.1. And so therefore this would be plus 0.1. And this one would be plus 0.1. So when it reaches equilibrium, everybody here is going to be 0.1 molar. And the HCl is essentially 0. So if we want to go back and say, okay, what's the H plus concentration? We just figured that out. So the H plus concentration is the same as the acid concentration, and it's 0.100 molar. The Cl minus concentration, which is not going to affect the pH at all, is also 0.100 molar. And we want to say, so we're going to figure that one out. Now what's the OH minus? OH minus is equal to 1 times 10 to the negative 14, okay, divided by 0.1. Okay, and so we know that that's going to be 1 times 10 to the negative 13. Okay, so 1 times 10 to the negative 13. So the pH is 0.1. The pH is the negative log of 0.1 of the H plus concentration. And doing that in our head, remember that is 1 times 10 to minus 1, so the pH is 1. Because this is 3 significant figures here, then we should have 3 numbers out to the decimal point. Okay, on our answers we have 0.100 because it just feels more comfortable. But officially it's 3 decimal points afterwards. If that's our pH, then we know that the POH is 14 minus the pH. So in this case it would be 13.00, officially 13.000. And the other part here, if we wanted to figure out our percent ionization, okay, the percent ionization is how much, starting with this, how much of it has broken up, and it has all broken up, so we actually know the answer is 100%. If we wanted to show why, we'd say it's 0.100 ions have formed, starting with 0.100 molecules, times 100%, and that comes out to be 100%. Ionization, which is exactly what you'd expect for a strong acid. So we have gone through, we figured out our H plus, just because it's the same as the HCl. We calculated the pH, we calculated the POH, we calculated the OH minus. So once we know any of those, we can find the others. And we figured out our percent ionization. Okay, second example is another strong, okay, this time it's a strong base. And so we're going to have totally breaking up. So starting with calcium hydroxide, solid. This breaks up, single arrow, into calcium ions and hydroxide ions. And even though this doesn't totally break up, it's for this percentage, it's going to be, we're consider it all broken up. So if we do our icebox, okay, we start with a 0.1 molar solution and 0 of anything else. Okay, again, we're going to say that this all breaks up, so this would be positive 0.100, and this one is positive 0.200, So this is 0.200 molar, and that's important because the OH minus concentration is going to be what affects our pH, and the calcium hydroxide would be 0. So again, if we want to go back and say, well, what do we know? We know that the calcium ion concentration is 0.100 molar. Okay, our hydroxide ion concentration is 0.200 molar. And now we can either figure out our pOH based on this, or we can figure out our OH minus. Let's go ahead and do, H plus concentration. So if the H plus concentration is equal to 1 times 10 to the negative 14 divided by 0.200, this comes out to be 5.01 times 10 to the negative 14. Now we can also calculate, okay, our pOH. So the pOH is a negative log of our OH minus, which is 0.2. Okay, and the pOH in this case comes out to be about 0.70. And our pH will be 14 minus the pOH, which obviously will be about 13.30. So we've calculated our OH minus. Okay, that's the first thing we had to do, and it was not this original calcium hydroxide. We had to double it, so that's the first thing we had to determine. And once we know the OH minus, we can find the pOH. Okay, we can find the pH, we can find the H plus concentration, and now we need to do our percent. And our percent, okay, we're going to use this number and this number. Okay, so the amount that breaks up, and again, we can see what's going to happen. It's going to be 100%. So 0.1, okay, of this breaks up, starting with 0.100 molar, okay, times 100, and so obviously that's 100% dissociation, which again is the definition of strong acid or strong base. Okay, example 3. This time we're talking about a weak acid. And we should recognize this as a weak acid. Okay, it's acetic acid because it's not one of our H-strong acids. So that means when we calculate the H+, which is our first step, we're not going to do this directly. We've got to do this with an icebox. And just like we've been doing in the other chapters. So let's start off with an equation, HC2H3O2, and this is aqueous. Okay, breaks up to give you H+ and C2H3O2 minus. And notice again, this has a double arrow because now we're talking about an equilibrium. And we're starting with 0.100 and 0 and 0, that's the same. But this time, we have to say X of this breaks up. We don't know how much it's going to break up. Okay, X, and if that's X, this is plus X, and this is plus X. So we have X, we have X, we have 0.100 minus X. Now the second clue we have is the Ka, and the Ka expression is going to be the products over reactants, concentration of H+ times concentration of acetate all over the acetic acid. And that equals 1.8 times 10 to the minus 5. So you can see what's going to happen. We're going to substitute in X and X, so X squared over 0.100 minus X, and that equals 1.8 times 10 to the negative 5. And that is going to result in a quadratic equation. So we're going to go back and say, well, let's assume, and it's a good assumption, that X is much smaller than 0.1. Therefore, 0.1 minus X is pretty much the same as 0.1. So that simplifies our expression over here into X squared over 0.1 equals 1.8 times 10 to the negative 5. And just by multiplying both sides by 0.1, we get X squared is equal to 1.8 times 10 to the negative 6. Now, we're not really interested in X, in X squared, we're interested in X. So that's going to be the square root of X squared. That's going to be the square root of 1.8 times 10 to the minus 6. And then one thing that I really like to do here as a safety factor, and that is, what is X representing? And X for here is representing my H+ concentration, And that's important because, sometimes the X is going to represent the OH minus, sometimes the H plus. Okay, so my H plus concentration is 1 times square root of 1.8 times 10 to the minus 6, which is equal to 1.3 times 10 to the negative 3 molar. That's my H plus concentration. Now, once I know my H plus concentration, then I can do all my other strategies, get my OH minus, get my pH, get my POH. And let's go ahead and do our percent ionization while we're here. And that is we want X, that's how much dissociated, over the 0.1. And we know the value of the X is 1.3 times 10 to the minus 3. So my percent is going to be 1.3 times 10 to the minus 3 molar over the starting value 0.100 molar times 100. Well, 0.1, 10 to the minus 3, 10 to the minus 1, that's 10 to the minus 2 times 10 to the 2, that all comes out to be 1. So my answer is 1.3%. So our vinegar, our acetic acid solution, is dissociated to the tune of about 1.3%, which is what we usually say about, a weak acid between 1 and 5%. Now let's go back and finish our problems. Okay, we know our H plus concentration, so we can figure out the rest of these. So the OH minus concentration is 1 times 10 to the negative 14 divided by our H plus, which is 1.3 times 10 to the minus 3. That comes out to be 7.4 times 10 to the minus 12. Okay, back at the top here. Okay, we could have also calculated our acetate concentration, and our acetate concentration is the same as our H plus concentration. It's also X, so it's 1.3 times 10 to the minus 3. Okay, so there's our OH minus concentration. So we can figure out the pH, and the pH is the negative log of the H plus concentration, 1.3 times 10 to the minus 3. Now, just estimating, we know that that's going to be between 3 and 2. And when we calculate it, we find out it's 2.87. And our POH is 14 minus the pH. And so 14 minus 2.87 comes out to be 11.13. So we figured out our POH, we figured out our pH, we figured out our OH minus concentration, we figured out our H plus and acetate concentrations, and again we've calculated the percent ionization. So that's all the information we get from example 3. Example 4 is similar, okay, but this time here we have a weak base. Now, since it's a base, then we're going to start with try to calculate the OH minus concentration. And again, in order to do that, we're going to need an ice box. We'll be using the Kb of ammonia. And then once we get the OH minus, then we have, free reign. We can get the H plus concentration, we can get the POH, we can get the pH. And once we know X, which is going to be our OH minus concentration, we can figure out our percent. But the first strategy here is to get the OH minus concentration using an icebox. So that means we need to have an equation. Now NH3, okay, it's a base, which we know is a proton acceptor. So we have to show some kind of a donor, and that's what our water is, something that's going to donate an H plus, and it becomes NH4 plus OH minus. Now just down here, we should remember that NH3 looks like this, and it has that lone pair. And that lone pair is very important because that's where an H plus ion can come and bind, and so that's where we get the NH4 plus. So the NH3 is before it binds, and then the NH4 plus is after it binds. The NH3 is our base, and the NH4 is going to be our conjugate acid that's going to come on this. But that we don't need that information right now, but it's all true. So I'm going to go back a little bit and get back to our calculation. So we want to do an icebox. And this icebox is going to look very similar to ones before, except we have water in here. And it turns out that water, I didn't write it that way, but water is a liquid. So it does not show up as part of our expression. So we're going to say our Kb concentration of ammonium times the concentration of hydroxide over the concentration of ammonia, and we don't include the water because it's a liquid, and the value we're given here is that this is 1.8 times 10 to the minus 5. Okay, so what do I have? I have 0.1 molar, just like we did before. We're going to say x of this goes away, so we're going to make x and make x. We have x and x, 0.100 minus x. So at this point, this looks exactly like the problem we had before. And we can see what's going to happen. We're going to get x squared over. So we're going to say, can I make that assumption? Yes, I can. So assume that x is much smaller than 0.100. Therefore, 0.100 minus x is about the same as 0.100, which means this math question turns into something much simpler. And the only difference here is that when we do this problem, we're going to say x squared is equal to 1.8 times 10 to the minus, that's a 5, 10 to the minus 6. And again, I'm not interested in x squared, I'm interested in x, so I take the square root of both sides. So this equals 1.3 times 10 to the negative 3. We've seen that before. But the big thing here is, what is this x? And this x we can see is ammonium and ammonia on hydroxide. So this is our hydroxide concentration, which is what's important for figuring out our pOH and therefore our pH and all that stuff. However, it also equals our ammonium concentration. Okay, which is just good for the problem because it says figure out the concentrations of everything. And we need to go back too and say, well, what is our ammonia concentration? Our ammonia concentration is not 0. Okay, so the ammonia concentration, I think I forgot to do this on my last example, is 0.100 minus, 1.3 times 10 to the minus 3. So it's going to equal 0.099, maybe 9. Okay, it's pretty high molar. Okay, let's finish things off. Now that I know my hydroxide ion concentration, I can do several things. I can figure out my H+. I'm going to go ahead and figure out my pOH. So my pOH is negative log of my, I'm going to clean that up. Okay, the pOH is the negative log of my OH minus concentration, 1.3 times 10 to the minus 3, which means that that's going to be somewhere between 2 and 3, and which is similar to the problem we did before. It's 2.87. And if I know my pOH is 2.87, then I know my pH is 14 minus the pOH. So 14 minus 2.87 will be 11.13. And my H+ concentration, again, I can get that either by saying 1 times 10 to the minus 14 divided by this number, or I could say that it's 10 to the negative pH. Either way, the answer does come out to be 7.4 times 10 to the negative 12th. So I know my H+ concentration, I know my pH, I know my pOH, I know my OH minus concentration, which is also the ammonium concentration, and by doing the subtraction, I was able to find my NH3 concentration. Now my last little step then is what's the percent ionization? And so this is the amount that broke up, that's X, which will go back here, this value, divided by this value. Okay, now this value here, this X, it can also use this one and this one, they're all the same X. So it's 1.3 times 10 to the negative 3 molar, over what we started with, 0.1 molar, times 100. And again, like we saw before, 10 to the minus 3 divided by 10 to the minus 1 is 10 to the minus 2 times 100, which is all makes that all 1. So again, this one also is breaking up about 1.3%. And that's examples 1, 2, 3, and 4.